Okay, so we are going to start mainly the part concerning sampling theory. So what we are going to do in a nutshell, okay, in this session is to see how it is approximate, in fact, the expectation and the variance of a random variable from observations. Okay. And the first part of the session will be devoted to general considerations. Okay. And after, we are going to see what will happen, okay, in the case of Gaussian random variables, because in the case of Gaussian random variable, we are going to see that we have very nice features, okay, concerning this distribution, and you will see the link, okay, between these questions and the chi-square distribution, the student distribution, and also the F distribution you have studied during the homework, okay, and that's why I have given to you the homework. And I remind you that the correction of the homework is available on my website, okay. F and student have a link with, okay, how to approximate mean and variances of Gaussian random variables. Okay, so let's start with this part of the course. I will split my screen. Okay. Let's start from the beginning. Okay, so you have some references here if you want, but keep in mind that on my website you will have, okay, the videos, the slides. You have also that is already available, okay, the list of the exercises with the correction. I will record a video for the correction of the exercises, but already you have the correction, okay, that is paper. Okay, so first we are going to introduce, okay, some let's say some vocabulary. So in sampling, and more generally, okay, in estimation, we are going to be interested in, okay, deduce some features of a population, of an experiment, okay, using, okay, what we are able to observe, that is in general, okay, particular subset of the population, okay. So deduce from particular observations some feature about general observations and being able to make the link concerning these two things, okay. So the first thing we are going to define, okay, it's the name, okay, it's the notion of random sample, okay, that is this one. So a random sample will be simply, okay, for us, I just connect my pad. So a random sample so what is a random sample? It's just, okay, a set of independent, it's independent random variables with the same distribution. It's what we call a random sample. You have n independent random variables, okay, with the same distribution. Sometimes, okay, something that is equivalent to say that x1, xn are d random variables. What is the meaning of IID? The first I is for independent. I want the independence as here. And ID here means and identically distributed. So identically distributed means simply that they have the same distribution. Okay, so to say that I have a random sample or ID random variables will be just a question of vocabulary. It means the same thing that you have in independent random variable having the same distribution. Okay, so if you come back to the example, okay, in the little video concerning the introduction of this session here, okay, when I have flipped the coin several times, okay, so I do independent flipping of a coin, then what I observe is exactly a random sample, because you have, okay, observations of independent random variable that have in this case the same distribution, that is a Bernoulli of parameter P, where P is the probability for a head to occur. Okay, so what we have done in the introduction was a special case of this definition here. So just a remark concerning this, okay, so of course I have independent with the same distribution. So I know that, suppose that you are in the case where the random variables are jointly continuous, okay, then you know that in this situation, the density of the n sample here, that is a mapping depending on n variables, may be written as a product, okay, it's a product because of independence. So here is just the independence that I use here, but then, so I have a I know that they all have the same distribution. In this situation, to have the same distribution just means that they have the same density function. So I can write it this way. I can write x1 here instead of xi because they have the same density. This one, okay? So for example, okay, if I have n sample or IID exponential of parameter lambda with a lambda that is strictly positive, then the joint density of the n tuple can be just written as the probability for the product, excuse me, 1n of the density of an exponential of parameter lambda. So it is lambda exponential minus lambda here xi, indicator function xi that is positive, okay? And something that I can write this way here. So it is lambda to the power n. The product of the exponential gives the exponential of the sum. So I can write it this way, minus lambda, the sum from I equal to 1 to n of the xi. And then I don't have to forget the indicator function, okay? So excuse me, it's not a big xi here, it's a small xi. And the same occurs here. And x1 greater than 0, indicator function xn greater than 0. I want all of them to be greater than 0. I want all of them to be greater than 0, okay? And something that I can write here if I want to, the indicator function of the minimum of the xi greater than 0. Okay, they will be all greater than 0 if the minimum is greater than 0. Okay, so I have this. So you have this expression in the case of an n sample of an exponential of parameter lambda. I can also give you an example in the discrete case, for example, because here my definition, I just write the case where, okay, I have density functions, but of course I can adapt the definition in the case where, okay, you have discrete random variable. So if you are in the discrete case here, what is the analogous of this one? So here, everything is expressed using density. Okay, here I can write that the probability mass function of the n tuple has to be equal to the product of the probability mass function of each component. And since I know that each random variable in this situation have the same probability mass function, I can write this in the following way. P of x1 equal to xi. Okay, because x1 and xi have the same probability mass function. If I take an example, suppose that you have IID Bernoulli of parameter P. So meaning that I am in the situation of my little introduction. I flip a coin several times independently, okay? And xi represents, okay, 1 if head, 0 otherwise, okay? So I obtain here Bernoulli of parameter P, where P is just the probability for head to occur, okay? So if I do the job in this situation, so just remark that here, the probability that x1 is equal to x, so I know that, okay, this one is equal to P if x is equal to 1 and is equal to 1 minus P, okay, so just write this, okay, it was P if x is equal to 1 and 1 minus P if x is equal to 0, okay? And in fact, I can write this expression, okay, using this compact notation. So it is P to the power x, 1 minus P to the power 1 minus x, indicator function x belongs to 0, 1. Of course, because when x is equal to 0, I obtain 1 minus P here, and when x is equal to 1, I obtain P exactly in this situation. So it means that the probability mass function of the n tuple here the probability of n tuple in this situation is just the product I equal to 1 to n, okay, of what? Of P to the power xi, 1 minus P, 1 minus xi, indicator function that xi belongs to 0, 1, and something that I can express if I want in a little better way. So here you will have P of x1 times P of x2 and so on. So you have P of the sum of the xi. Okay. Here you have 1 minus P to the power 1 minus x1 multiplied by 1 minus P to the power 1 minus x2 and so on. So I have here 1 minus P n minus the sum of the xi, and then I have the product of the indicator functions, okay? And you will see that this kind of expression will be used, okay, in the following part of the course. Okay, so just a random sample, if I come back, okay, is just, okay, a family of independent random variables having the same distribution. So in the case where they have density functions, I am able to obtain the density of the n upper, okay, and in the case where they are discrete, okay, I can obtain the probability mass function of the n upper. Okay, so I have just this. Second definition, what we call, okay, a statistic or an estimator. And I will use mainly the word estimator in the following, okay? So what is this? It is a regular function or a regular mapping of a random sample. Okay, so just see what happened, okay? So I just do this, 1 second. So in fact, we are going to approximate quantities with estimators, okay? So what will be an estimator? Will be something of this form. F, so maybe I will take another notation because F was for the density function here. So let's write H of x1, xn, where H is regular. And by regular, I mean, so for you, everything will be regular, but I will have something H, okay, that is, let's say, of class C1, okay? And mainly you will see that in most of applications we are going to do, okay, H will be a polynomial, in fact, of several variables, meaning that here I have a polynomial, okay, in the x1, x2, xn, okay? So let's see an example we have seen together. So in the case of my little introduction, when I flip the coin several times, okay, I have approximate P, okay, by the average of my observation. So here you have an estimator that can be written this way. Okay, and you are going to see in the next slide that this one will be called the sample of the sample mean, excuse me, related to my sample. So this one, okay, that I will call just after the sample mean. And just take, so you take this form because it is equal to h of x1 xn, okay, with h of x1 xn equal to 1 over n sum of the xi. So you have here a polynomial of order 1, okay, polynomial in this situation. So concretely, okay, an estimator will be something that may be built from the observations, that is, that may be built from my n sample, okay, x1, x2, xn, okay, just through a mapping H that is regular, okay, and I give you an example here. And in this course, in the course concerning sampling, okay, our objective will be to build, okay, estimators of the expectation and of the variance. It will be the aim of this first, okay, course of statistics, okay, find estimators for expectation and for the variance. Okay, so it's what we want to do in this course. Okay, so we are going to introduce, okay, a final definition here in this situation. That is a generalization, in fact, of what I have done in the case of the introduction where I flip my coin. Okay, so it's the definition A3. Okay, so I defined the R sample moments of a N sample and the related R sample moment about Xn over line that I will define just before. That is, okay, if you want the centered sample moment. So let's explain, okay, you will see that it's really basic. Okay, so let's explain the meaning of this slide here. So when everything is well defined, okay, I have seen that previously I have approximate my expectation, okay, by 1 over n, the sum from I equal to 1 to n of the xi, okay? And with this definition 1, okay, it's what I called here the sample mean, okay, and that I denote by xn over line, okay? And we are going to spend time on study the property of this one. So this one, that is an estimator, okay, because it is just a regular mapping of the xi, okay? So you have an estimator that will be, in fact, an estimator of the expectation of a n sample. Okay. So of course, when I write this, okay, if the moments are well defined, that is, if you have, for example, expectation of x1 to the power r, using the same notation than the one I have used here, but of course, if this expectation is finite, that is, if my x1 belongs to L to the power r, I can approximate, so I have just an expectation here, so I can use this ID, and okay, I denote this approximation this way, the sum from I equal to 1 to n of xi, okay, to the power r, okay, so it's exactly the same idea here. I just give a name to this one, that is m for moment, r for the fact that I take r equal to the power r here, okay, and of course I have here xn over line that is none other than m1, okay, so I have this. So you have here, okay, approximations or estimators of the expectation of the power of a random variable, okay, based on an n sample. And the most interesting one will be, okay, here the will be the sample mean, that is the estimator of the expectation, okay? So I have this one for the expectation and what we call the R's moment of the random variable. And here I have the R's sample moment. And for R equal to 1, I recover exactly the sample mean. Okay, so let's continue with this definition here. If I am interested in the variance of x1, okay, what is the variance? It is the expectation of x, okay, minus the expectation of x squared. Okay, I have this one. And the way I can approximate this one with my observation is to say the following. So I know that if I have the expectation of y squared, okay, using what I have done previously, I can approximate it with M2, that is 1 over n sum from I equal to 1 to n of yi square. Okay? So I can do the same for this one here, but just keeping in mind that this expectation here may also be approximated by the sample mean, in fact. So this one approximated by the sample mean. And if I use both IDs here, I can say that the variance may be approximated in the following way. So 1 over n, that is the one here, sum from I equal to 1 to n of xi minus xn overline square. This one is called the sample variance. And will be denoted by sigma n square. Okay, so it means that from an n sample, you will be able to find such an estimator, and we are going to study its properties just after, okay, of something that is the variance from my observations, that is from the elements of my n sample that are the x1, x2, xn. Okay? I can generalize this ID. I can generalize this ID to obtain what I call the R sample moment about xn overline. Huh? Okay, so when you have here the about xn overline, it just means that here the expectation is approximated by, okay, the sample mean. So I can do exactly the same for this expression of this type here. To the power r. So in the case where r is equal to 2, you obtain the sample variance here. But when r is equal to a number strictly greater than 2, so here keep in mind that if I take r equal to 1, I obtain 0. So it's something that is not interesting here. Huh? But I can approximate it, okay, for r strictly greater than 1, okay. By what? Using exactly the same ID, 1 over n, sum from I equal to 1 to n of xi minus, by replace the expectation by the sample mean. And I have this one. And of course, if I denote this one by mr prime, that is the R sample moment about xn over line, yes. Then, okay, for r equal to 2, I obtain the sample variance. Okay. So, and the aim of what we are going to do just after will be to study, okay, some nice features about the sample mean and the sample variance. Okay, so we are going to start to do it in rich generality at the beginning. Okay, so I will be able to say things about these estimators. Okay, and then in the particular situation where x1, x2, xn are IID Gaussian random variable, that is that I have an n sample of a Gaussian random variable, I will be able to find more interesting properties in these particular situations. Okay, so first, what happened for a general distribution? We will see things that are interesting by themselves. Okay, and then, okay, to go more deeply in the details, see what happened in the case of Gaussian, and it's here that we are going to recover the interest of the chi-square of the F distribution of the student distribution that we have studied together. Okay, so let's continue. So here we are going to to study the properties of the sample mean. okay? So I give a name for the expectation of my random sample. So here you have IID random variables, independent and identically distributed. You do no hypothesis concerning the distribution, except I want them to be in L2. L1 is sufficient to define the expectation, but I want to deal also with the variances, okay, of this quantity, and you are going to understand why just after, okay? So let's do the job in this situation. You will see that in this situation, the things are very basic. Okay. So what can I say in this situation? So my mu, that is the expectation of x1 here, will be approximated using the sample variance, the sample mean, excuse me. This one, okay? First, we are going to be interested in the expectation of xn over line. But here it's very basic because I have the expectation of a linear combination, that is the linear combination of the expectation using the linearity of the expectation. And I know that I have an n sample, meaning that all the expectations are the same because they have the same distribution. So I have here, in fact, 1 over n, sum from I equal to 1 to n of mu, that is simply equal to mu. Okay, so the result is the following, that the expectation of xn over line is equal to mu. Okay. So what is the meaning of this one? From an intuitive point of view, it means that, okay, I want to approximate my mu by this estimator here. That is the sample mean, the sample mean I am interested in. And what I know from this relation is that in expectation, my sample mean is equal to mu, meaning that in average, what I do is a perfect approximation because in average, my estimator, okay, is equal to the parameter of interest. Okay. So I have this relation that is a basic one and that you have to know. Okay, so starting from an n sample, my sample mean has an expectation equal to the expectation of each random variable, that is mu in this situation. We are also going to be interested in the variance of xn over line. So what is the variance in this situation? So I have the variance of a linear combination. So a priori, in general, it's complicated to compute. But here, keep in mind that I have independent random variables. So I can remove first the 1 over square because I have 1 over n in the definition of xn over line here. And then I have the variance of the sum. But here, by independence, the variance of the sum is equal to the sum of the variances here by the independence. And I know that all these variances are equal because I have an n sample. The n random variables have the same distribution, so they will have the same variance. So I can write, so be careful, okay, because here I have n squared, so it's an n squared here. And I obtain, so here the sum of all these terms is just n times the first one, and I obtain the variance of x1 over n. And I write my results in green here. The variance of xn over line is equal to the variance of x1 over n. So something that you have to know, okay, and have a look on the fact that these relations are true only using the hypothesis that I am independent with the same distribution, okay? And that the variance exists. So these relations are true independently of what is the precise distribution of my n sample. So I can use it in the case of a Poisson, in the case of an exponential, in the case of, okay, gamma, and so on and so on. Okay, so I have this. So let's have a look on what would be the interest of this quantity. So what I have here, I have this one, yes, sample mean that I keep. So suppose that you are in this situation. Suppose that you have T that is an estimator of the mean I am interested in here. Okay? My question here is to measure the quality of the approximation that is in a sense that I have to precise, okay, then I want to measure in some sense the distance between T and mu. But I remind you that at the end of the course concerning random vectors, if I remind, okay, I have defined the following, D, okay, that is something on L square times L square into R plus that associate to two random variable in L2 here. What? The expectation of the difference of the square to the power 1/2. And what we have proved together, we have done the proof. It was, okay, an application of the Cauchy-Schwarz inequality. We have done D is a distance on L2. And here, typically, my estimator, okay, I suppose it to be in L2. It's the case of my situation here, because if x1, x2, xn are in L2, my sample mean, okay, I keep in mind that here my xn over line for sure belongs to L2 by linear combination and knowing the fact that L2 is a vector space here. Okay, so it means that in order to measure the quality of my approximation, okay, but I can try to compute the distance, okay, between T and mu. Okay, so, and as you see here, in my definition of the distance, I have a square root here, okay? So instead of using the distance, because I don't want to handle a square root, okay, here, I will take the square of the distance, okay? So, and my idea, if it's possible, it's to minimize this distance, and you know that minimize a number or, okay, that is positive. So here I am in R plus. A number that is positive or is square, it's totally equivalent, okay? So if I write this one, okay, I can write this one as the definition, the expectation of T minus mu square. And we are going to express this quantity in this way. I can make appear the expectation of T here. But if I do this job, of course, I have to add it. And then I will have two quantities, okay, that we are going. So I will have this one, and we are going to develop the square here. If I do the job, I obtain what? I obtain the expectation of T minus expectation of T square, okay? That is the expectation of A square here. So I obtain the variance of T, okay, here. plus what? Plus b squared, okay, the expectation of b squared, that is plus, so here you have a number. It's not a random variable here, it's a number. So I have plus, in fact, b squared, that is the expectation of t minus mu square, and then plus 2 times this one, the expectation of t minus the expectation of t, and expectation of t minus mu. But here I have a number that I can remove from the expectation by linearity, and it remains the expectation of t minus expectation of t. And of course, I obtain for this quantity 0. So if I summarize what I have obtained here, okay, the square of the distance between t and mu is equal to the variance of t plus the expectation of t minus mu square. So you see that if you want to control the distance between my approximation and what I want to approximate, I have two things to control. I have to control the variance, okay, and then I have to control the square of this quantity. I give to this quantity a name here. This one, what I have inside the square, is called the bias. The bias is what? Okay, you want to approximate mu by t. The bias is just the expectation of t minus mu. Okay, that is equal to the expectation of t minus mu. So this is the bias here. Okay, so that is in some sense the error you do in average. Okay, the error you do in average. And here it's the variance of the estimator. So if I come back to my case, that is the case of the sample mean. So in the case of the sample mean, what happened? So I can erase this computation here. And in the case of the sample mean, so when t is equal to xn over line, and what I know, if I want to compute this term in the case where t is equal to xn over line, okay, in this situation, I have a bias that is equal to 0. We say that in this situation, xn over line is an unbiased estimator of mu. Okay, an unbiased estimator of mu, because the bias is equal to 0. Unbiased, bias equal to 0. If I want to compute the square of the distance here, so if I am interested in the square of the distance, and I remind you that the square of the distance here is just equal to the expectation of t minus mu square, okay? But this one will be in this situation, so the bias being equal to 0 will just be the variance of xn over line. And that's why I have previously computed this variance, and I obtain in my situation by my previous computation that here, this one is equal to the variance of x1 over n. Okay? I will introduce another name. So for the square of the distance here, we are going to call it here MSE, that is the mean squared error. So here I have introduced this vocabulary in the case of the sample mean, but of course it's vocabulary that we are going to use, okay, in the next session, because, okay, it's something that is independent of the sample mean, but just related to an estimator, okay, that is with the property that this estimator is in L2 in order to be able to compute variances, okay? So in a general situation, my mean square error, okay, that is this term here, will be equal to the variance of the estimator plus the square of the bias. In the case where I have an unbiased estimator, then, okay, the precision in terms of mean square error of my approximation will be just controlled by the variance of the estimator, okay, by the variance of the estimator. In the case where I am unbiased, the mean square error is just the variance of my estimator. So just have a look on this one here. Okay, so in the case of the sample mean, if I come back to the sample mean, I have my mean square error that is equal to this one. I can do two situations. I can say two remarks here. Of course, I see that this term goes to 0 when n goes to plus infinity. And in fact, even when n increases toward plus infinity, the mean square error decreases toward 0. And it's that natural here because what you do, I approximate my mu using observation, x1, x2, xn. If I increase my number of observation, okay, I remark here through this computation that I will have a precision that is better and better. And to be theoretically infinite, an infinite precision that is an error equal to 0 if I allow for infinite random samples, okay? So I have this. Second remark, I start from x1, x2, xn that are in L2 and I want to approximate their mu, okay? They are in L2, so they have a variance, okay? They have a variance that is equal to the variance of x1 here. And I see that, okay, if I work with a fixed number of observation, the sample means is more precise when the variance of my random sample is small, because here the error is equal to the variance over n. If I fix n, okay, but the error is controlled by the variance. So if I have a small variance, I will have a better precision than if I have a big variance. And it's that normal because keep in mind that I have explained to you that the variance is a way to control, okay, the distance between a random variable and its mean, okay, a random variable and its mean. So if you consider the sample mean, it will be intuitively a good approximation of the mean if the random variable is well approximated by its expectation, okay. And the critical case is when the variance is equal to 0. When the variance is equal to 0, it means that my error is minimal because it's a positive number that is minimal for 0. But in the case where this error is minimal, it's the case where the random variable is simply constant. Okay. So I have this, okay, and this sample mean case was a pretext in order to do what? In order to introduce the notion of mean square error, the notion of bias, okay, and to see that in the unbiased case, the mean square error is none other than the variance of the estimate, okay. So let's continue with this precision with the last remark, okay. So the mean square error of an estimator, I have written it to be, okay, the expectation of t minus mu square. If you know the mean square error, as it's the case in the case of the sample mean, because in the case of the sample mean is in unbiased, so this term is 0, and the mean square error is just the variance. Okay, so when the mean square error is known, from the Chebyshev inequality, keep in mind that the probability that t minus u is greater than epsilon is less than what? In fact, the mean square error over epsilon square. Okay, something that is equivalent to say that the probability that t minus mu is strictly less than epsilon is greater than 1 minus the mean square error over epsilon square. Okay? This probability here, so it's the probability that the error I do in absolute value is less than epsilon, and of course it may be controlled by the mean square error in this particular case, okay? Because the mean square error, okay, may be introduced using the Chebyshev inequality. Just a remark on the fact that this probability here, okay, can also be written as the probability that mu belongs to an interval that is an interval with that is centered around capital T and with size 2 epsilon, okay? And you have here a random interval. Okay. If I write the things in the case of the sample mean, okay, I can say that the probability that mu belongs to xn over line minus epsilon xn over line plus epsilon, okay? Or in fact, if I want to be totally clear here, my interval here, it's a strict inequality here, okay? So if I want to be totally okay, it's the open interval here, okay? This one, continue with this here, so it's also the open interval here, not the closed one. So this one, okay, is greater than 1 minus, so the mean square error that is just equal to the variance, in this case, that is the variance of x over n epsilon square. Okay, so you have a situation where you have here xn over line. You have around xn over line a little random intervals that has a fixed size, that is a size equal to 2 epsilon here, okay? And the probability for what I want to approximate to be in my random interval here is greater than this one, okay? And in general, you will see that we are going to fix this probability to be greater than a particular level. That would be for us in general 95%, but that can be 99% also, okay? So if I fix it to be, let's say 95%, but if I am able to compute the variance of x, if I am able to know what is the precision that is to control my epsilon, okay, I will be able to know, okay, which number of observation I need to have in order to obtain a particular level, okay? And typically here, let's see just a numerical case. Okay, so let's do this. So I erase this one. I keep this one, okay? And if you have, for example, so a numerical case of this one, if I take a variance equal to 1, why not? And if I want to have, okay, 2 epsilon, that is, for example, 0 0.01, okay? But to have 1 minus the variance of x over n epsilon square, that is equal to 95%. So I have this one. I will need to have n that is equal to what? So n that will be equal to, so I make this one here, and I obtain, okay, I obtain what? Variance of x over epsilon square multiplied by 0.05. And in the case where my variance is equal to 1, and in the case where, in fact, epsilon is equal to 0.005, okay, I obtain what? So let's do the computation in this case, okay. I have a calculator somewhere here. So I have to do what? So I have the computation already here. So, but what it was, okay, it was 0.005 square multiply by 0.05, that is equal to this one, and I have to take the inverse. Okay, so I see that in my situation here, let's come back to my, I obtain, in order to have a precision that is the size, okay, of the interval here, that is 0.01, I need this one to be equal to 800,000. Okay, so if you have this number of observations here, you will be able to obtain with a probability of 95%, or at least 95%, an interval here of length 0.01, okay, in order to approximate your mu by the sample mean. Okay. Okay, so here it's a classical way. So just a remark, because it can be the occasion to define, okay, something that is more general. Okay, so here I want to approximate mu. Okay, I want to approximate mu, and what I have done here, okay, is to build. So here it was an open interval, but whatever. I have built an interval, okay, for which the probability that mu belongs to this interval is equal or greater, okay, or equal or greater than, let's say, 95%. But of course, I can do exactly the same job here with 99%, or a probability that may be very near from 1. But of course, if I want something that is very near from 1, I will increase once again my number of observations needed to obtain a particular level, okay? And what I have for this interval, I see that the bounds of my intervals, in fact, are made from the observations. So in fact, here I have random variables, okay? I can call it, I have theta 1 of x1, xn here, and I have theta 2 of x1, xn, okay? And what I will give a name for this one, okay? This random interval for which mu belongs to this random interval, that is an interval built from the observations, is greater than to a particular level, okay, is called a confidence interval of level here 99%. So it means that with a probability equal or greater to 95%, my mu, that is the quantity I want to approximate, belongs to this random interval. Okay, so it's what we call the confidence interval. So confidence, excuse me, interval. I have forgotten the interval here. Of level 95%. And I see that in this situation, okay, I will be, if I have the mean square error, okay, I will be able, using the Chebyshev inequality, to compute in general, okay, a confidence interval. But as we are going to see in the next part of the course, that if not the next part, but the end of the 2-day session, okay, then I will see that this way to build the confidence interval is not that optimal. Okay, and we will see this in the case of a Gaussian random variable, to see that in fact I need, in order to obtain this precision, in fact 95% for the sample mean, okay, that approximate the mean. In the case of a Gaussian, in fact I see that I need less and less observation in this one, because this inequality here that is coming from the Chebyshev inequality is not that optimal. Okay. So I have this for the sample mean, okay? That was the pretext to introduce the notion of bias, the notion of mean square error, and the notion of confidence interval, okay? So let's continue with this part of the course, okay? So keep in mind that for the moment, I repeat that I don't do precise hypothesis on the distribution of my observations. I have an n sample of a distribution, a particular distribution, but I don't know what this distribution is. Okay. So here we have dealt with the mean, okay, the sample mean as an approximation of the expectation. And now we are going to introduce, okay, some approximations of the variance. And we are going to do this in 3 steps, in fact, okay? First, we are going to have a look on what I call the ideal, okay, the ideal sample variance. And we are going to explain why it is called ideal sample variance. So what I want to do in this situation, so in this situation, okay, I have a n sample, x1, xn, okay, a n sample. I want them to be in L4. I want them to be in L4 because we are going to approximate their variance. So first we want that the variance is well defined. So I need to be in L2. And then, in fact, in order to control the precision, okay, I will need to have to take the variance of something that is an approximation of a variance. So variance of a variance. So I will have terms in the form of x to the power 4. So that's why I need them that the expectation of x1 to the power 4 is finite. Okay, so I have an n sample, okay, of a particular distribution that fulfills, okay, these expectation conditions for the moment of order 4. So I am interested in approximating the variance of x1 with the variance that is just, okay, the expectation of x1 minus the expectation of x1 square. Okay. What I call the ideal sample variance is this quantity. Put a tilde, sigma n squared tilde. It is equal to what? It is equal to 1 over n. So in fact, I have an expectation that I will approximate with the sample mean, in fact, okay? So it will be 1 over n, the sum from I equal to 1 to n xi minus mu square. Okay, so it's what I call the ideal sample variance. Why I call it ideal? It's because that if I want to compute this, practically, I need not only to know what are x1, x2, xn, so I need to know what are my observations, something that I have classically to know if I want to approximate something by an estimator, but I need also to know mu. Mu, that is the expectation of x1. Okay, so this mu has to be known. If I don't know mu, I won't be able to compute this term in practice. So I won't be able to approximate this one by this estimator. Okay. So I call it the ideal sample variance because in order to compute it, I need to know mu. And in practice, in general, it's a situation that more or less never occurs. That is, when I want to approximate a variance, in general, the underlying expectation is not known. Okay, but at this stage here, we are going to suppose that it is possible to know the expectation. Why not? Just to study what may be the properties of this estimate. Okay, I'm interested in this one. We are going to compute the expectation to control the bias of this estimator, and then the variance in order to have the mean square error, that is just the variance of the estimator plus the square of the bias. Okay, so let's compute expectation of sigma n square tilde. So by linearity of the expectation, I obtain 1 over n, the sum from I equal to 1 to n of the expectation of xi minus mu square. Here you have simply by the variance, sigma square, because they have the same distribution, so they all have the same variance here, that is denoted by sigma square, and I obtain here sigma square. So I can say that sigma n square tilde is an unbiased estimator of sigma square. Okay, so it means in these situations that if I am interested in the mean square error, the mean square error will be simply the variance of sigma n tilde square, because the bias is equal to 0. Okay, so let's compute the variance here. So I have a variance of a linear combination. So variance of this term with the 1 over square that I can remove from the variance, putting 1 over n square. And then I have the variance of a sum, that is in the case of the independence, the sum of the variances. Okay. I know that all the terms here are equal because the xi have the same distribution. So, okay, these variances will be the same because what I have inside, okay, are independent, so, but identically distributed random variables. So I obtain here 1 over n, the variance of x1 minus mu square. And what is this? You can see simply by a basic computation. So you apply the definition of the variance, the expectation of the square of this quantity. So I will obtain the expectation of this quantity to the power 4, expectation of this quantity to the power 4, minus the expectation of the square, okay, to the power 2, that is the variance to the power 2. So it's exactly that what I can denote by mu 4 minus sigma to the power 4 over n, where mu 4 is just the centered moment of order 4 because it's the one obtained if I take the expectation of the square of this quantity here. I have a power 4 that I obtained that will give me this term minus the expectation of the square that is the variance. So that is minus sigma square to the power 2, that is minus sigma to the power 4. Okay? So the variance in this situation is given by mu 4, that is this quantity here, okay, minus sigma 4 over n. And in general, okay, if I give you a particular distribution, you will be able to compute this quantity if I give you a particular distribution. So typically, mu 4, we will see that mu 4 will be equal to 3 in the case of a n01, for example. Okay, so mu 4 will be equal to 3 in the case of a n0. So I have the mean square error in this way because I have the variance of my estimator and because, okay, the estimator is unbiased, okay? So it's a theoretical computation in this situation because I repeat that in general, I don't know mu, okay? In general, I don't know mu. So it means that in general, I have a theoretical approximation of the variance by the ideal sample variance, but that I am not able to use in practice because in general, mu is unknown, okay? So let's see how to overcome this problem. So just have a look on the fact that if you are in this ideal situation, you are in the case where you have the mean square error and doing exactly what I have done for the sample mean and the mean, okay, I am able to build confidence interval for the variance in this situation, okay, exactly using the Chebyshev inequality as I have done here, okay, it's exactly what I have done here. You can do exactly the same for the variance because, okay, you have, okay, something in relation with the mean square error. Okay, so if you do the same that I have done here for the sample mean and the mu, if you take for t the ideal sample variance and for mu sigma square, okay, you have exactly this one that you can use. And I know explicitly here what is the mean square error. So I am able to build a confidence interval in this situation. Okay, so my problem is here that I have, okay, I am able to do something in the case of variance, but the price to pay in order to do this something is very high because I need to know the expectation. And in general, I don't know it. Okay, so let's see what we can do. So I have this one, okay. I don't need it, no, so I erase this one. Let's do this slide, okay, that will be the end of the first part of this session, okay? Because it will be the last general result that we are going to see together. And then from the next slide, we are going to see what happened in the case of Gaussian random variable, okay? But at this stage, I don't use for Gaussian hypothesis. So what is the principle here? Principle is that simple. My ideal sample variance is defined this way. But I said that to compute it in practice, I need to know mu, that is the expectation of x1. I don't know it in general, so the idea, it's the way I have defined, in fact, the sample variance, not the ideal sample variance, but it's to define or to approximate mu by the sample mean. And you obtain in this way what I have called the sample mean, the sample variance, excuse me, by approximating in the sample variance, in the ideal sample variance, okay, the mu by the sample mean. I have this one. Okay. So I want to study the properties of the sample mean, or the, excuse me, the sample variance. Okay. And first of all, I want to see if it is an unbiased estimator or not of the variance. Okay, so I am interested in the expectation of sigma n square. Okay, so by linearity, it is just 1 over n, the sum from I equal to 1 to n, the expectation of xi minus xn over line square. Okay, so just have a look on these quantities here. My expectation of xi minus xn over line square may be written as the expectation of what? Of xi, okay, minus 1 over n, sum from I equal to 1 to n, okay, of the xi square. Okay. If I define the following, oh, I will change my notations here. Just let me 1 second, okay, to be sure that I write it in the good way. This one. Okay, so maybe well, change nothing, but I will change my notation. Okay, to take here, I take just G. I define a mapping G of y1, yn that is equal to, in fact, y1 minus the sum 1 over n, the sum of yy. Okay, why not? Okay, I have this one. Why I do this? Because I see that xi minus 1 over the sum of the xi may be expressed as j of xi, okay? And I can write it this way, xi, and I will have here, okay, so something that I can write xi prime, where xi prime is just the vector x1, xn, except the coordinate xi, okay? So I have x1, xi minus 1, xi plus 1, xn, okay? So it's exactly this one. xi prime, okay, where xi prime is just the vector of the x1 of my observation, except the ith observation. So you have a x here, 1, until xi minus 1, xi plus 1, and xn here, okay, with points. Okay, so when I say this, and why I say this because, in fact, from this little remark here, this one. In this sum here, I have expectations to compute, okay? Expectation of mappings that I may be written this way. So I have here, inside here, just the square of this quantity. But the x1, x2, xn are independent and with the same distribution, okay? So it means that you see that when you define this one for a particular xi, in fact, you just have to change in this mapping, okay, but the name of the variable. So it implies that all these expectations are in fact equal. All these expectations are equal because x1, x2, xn are independent random variable, okay, having the same distribution. So all these one are equal, and then I can finish my computation here saying that here I have simply, in fact, the expectation of x1 minus xn overline square, simply. Because all these expectations are equal from the fact that I have, okay, this form for what I have inside in the expectation. So it's xi minus the average of all the coordinates. And I see that, okay, in order to obtain x1 or, okay, the value of this one for x1, the value of this one for x2 here, and so on, okay, it's just a kind of permutation in the coordinates of this mapping here, okay, giving to me the fact that all these random variables, so here, in fact, you have here id random variables, independent and identically, excuse me, mistake, what I do here, they are not IID because they are not independent, but they are just, okay, same distribution. So if I want to continue my computation here, if I want to continue my computation, for the moment, what I have written? I have written that the expectation of the sample variance is equal to simply the expectation of x1 minus xn overline square, where I remind you that xn overline is the sample mean, that is just 1 over n, sum from I equal to 1 to n of the xi, okay? I said the following: in order to express this quantity, I can express it this way. x1 minus mu minus 1 over n sum of xi minus mu square. Why? Because I have minus mu here, and in fact here, if I develop this one, okay, I can remove the mu from the sum, okay, and I obtain, okay, a simplification between these terms, okay. So I have this quantity that is equal to this one from the fact that xn overline is equal to this, okay. So I can write it this way, that you have xn, in fact, overline minus mu, that may be expressed as 1 over n, the sum from I equal to 1 to n of xi minus mu parenthesis here, simply. It's exactly what I write here. Okay, so I can write them here this way. y1 minus 1 over n sum yi square, okay, where the id random variables, and the big difference with the y and the x is that now, and that's why I do this job here, the expectation of yi is equal to 0. So in fact, in what I have done here, I just say that if I want to compute this expectation here, this expectation, I can always suppose that my expectation is equal to 0. The expectation of x1 is equal to 0, okay? So doing this little transform, I say that I can pass to the general case to the centered case, okay, just using this little trick here. Okay, so let's do now the computation. So I have yi that is equal to xi minus the expectation of xi here, okay? So let's do the computation in this case here, okay? So let's do the job. So I have what here? Now we are going to develop. We are going to develop, okay? We are going to develop the things. What I have written here, yes, it's this. So I am interested in the expectation of y1 minus yn over line square. That is exactly this quantity here. So let's develop, because I have a square. So I have expectation of y1 square, okay, plus the expectation of yn over line square, okay, minus 2 times the expectation of y1 y okay. Yn over line square. Okay, I have this one. I have exactly this one. Okay, and I want to be able to compute this quantity. So let's continue. So I erase this. So I write this one here and I continue my computation here. Okay, so I continue the computation here. Y1 is centered because it is x1 minus the expectation of x1. So here you have the variance of y1. That is equal to the variance of x. That is equal to sigma square here. Here you have, since the expectation of y1 is equal to 0, you have plus the variance of yn over line. We have seen together in a previous computation, it's what I have done, okay, in the part concerning the sample mean, that the variance of y1 or yn over line, by using the independence and the fact that they have the same, is equal to the variance of y1 over n, that is equal to sigma square over n. And then you have this term here that I am able to compute, and I will obtain what? I will obtain minus 2, the expectation of what? Of 1 over n, sum from I equal to 1 to n, y1, yi here. Okay, So something that I can express minus 2 over n, okay? Expectation, or in fact sum of expectation of y1, yi, okay? Sum over I here. Okay, but to compute this one, okay, I have to compute these quantities. The expectation of y1, yi. I said the following. If I is equal to 1, the expectation of y1, yi is equal to the expectation of y1 square. So this is the variance. So for the term I equal to 1 in this expression, I obtain the variance of y1. If I take I different from 1, what I obtain? In the case where I is different from 1, y1 and yy are independent. So the expectation of the product is the product of the expectation, and the product of the expectation is 0 in this situation, but because each expectation is equal to 0. So I say, in fact, that in this sum, I have only one term that is not 0. The term that is not 0 is the term for I equal to 1. And in this situation, this sum is none other than the variance of y1. So I obtain minus 2 sigma square over n. And finally, when I do the sum of these three terms here, I obtain what? I obtain sigma square minus, so sigma square over n minus 2 sigma square over n, that is minus sigma square over n. And I obtain n minus 1 over n sigma square. Okay, so the expectation of sigma n square is equal to n minus 1 over n sigma square. That is exactly the computation I have done here. Okay, so I have a problem here because I see that sigma n square considered as an estimator of the variance is biased. I have a bias that I am able to control because in expectation, I am not equal to sigma square. I am equal to n minus 1 over n sigma square. Okay? And that's why we introduce the corrected sample variance. We introduce the corrected sample variance, that is a modification of the sample variance in order to make it unbiased. So I define this one, that is just the sample variance multiplied by n and divided by n minus 1. But what happens if I compute here the expectation of Sn square? But it's n over n minus 1, the expectation of sigma n square. I plug inside this expression and I obtain sigma square. So I have something here that is unbiased. Okay, so what I do, I start from the sample variance. I want to compute its expectation in order to see if it is an unbiased estimator of the variance or not. I do this computation and I obtain what I obtain in red, that is, there is a bias, in fact, because the expectation of the sample variance is equal not to sigma square, but to n minus 1 over n sigma square. So of course, when n is large, n minus 1 over n times sigma square is not very far from sigma square, but it's not sigma square. So I have a bias that will be small if n is large, okay, but there is a bias. I don't want bias, okay, when I do estimation. So the idea here is to modify a little the sample variance in order to obtain a new estimator that we call the corrected sample variance in order to make it unbiased. It's exactly what I do in definition IA4, where I define the corrected sample variance, okay, just equal to n over n minus 1 times the sample variance, okay? And to conclude this part, okay, I just copy this board. I erase this computation here. So I have Sn square, that is an ambiguous estimator of the variance. So if I want the related mean square error, in this situation, it is just the variance of Sn square here plus by the bias square that is equal to 0, because you have the bias here. So it means that to compute the mean square error, I have to compute the variance. It's the aim of the theorem 1 that tell you that the mean square error in this situation, so it's the theorem is equal to what? 2 sigma 4 over n minus 1 plus mu 4 minus mu 4 minus 3 sigma 4 over n, where I remind you that mu 4 is just the expectation of x1 minus expectation of x1 to the power 4. That is something that you can know if I give you the underlying distribution. For example, I have said that in the case of Gaussian, you obtain here, in the case of Gaussian, you obtain mu 4 that is equal to 3, okay? In the case of n01 here. Okay, so I have this one because the variance is given by the theorem A1. So, okay, I want to do the proof of this theorem A1, okay? Not because the computation is complicated, because the computation is a little bit tricky, okay? So not nice to do, okay, on a virtual board, okay? But it's a good exercise to do at home, but not an exercise necessary to do, okay? So it's a good exercise if you want to see if you are able to compute, okay, expectations using properties of independence and to be identically distributed in a case where the computation is not that easy, okay? But I want you to know this result, okay? And I won't prove it, okay? If you are interested in the proof, okay? No special indication to give you, just, okay, compute. You compute an expectation, you develop what you have inside, and just use the properties of independence and identically distribution of your n sample, okay? The last remark I will conclude with is that, okay, a priori, at this time, we have an ambiguous estimator for the variance, okay, that is this one, and I am able to know what is its mean square error because I have its variance here, okay? Keep in mind that we have another estimator here that is the ideal sample variance that I have defined as sigma n square tilde that is equal to 1 over n sum xi minus mu square. And we have seen in our situation that the variance of sigma n tilde square was mu 4 minus sigma 4 over n, okay? And of course, I can see, and it's the aim of this remark here, that if you compare the variance given here by this variance here, then the variance of the corrected sample variance is always strictly greater than the variance of the ideal sample variance, meaning that the mean square error you do when you use the corrected sample variance will be strictly greater than the mean square error you do if you use the ideal simple variance. So in some sense, okay, if I compare this estimator, the ideal sample variance has a mean square error that is lower. So I have a priori an estimator that is better, but the price to pay is that in this situation, I am not in general able to compute in practice the ideal sample variance because I don't know mu. So, okay, the ideal simple variance in the case where I am able to compute it as a mean square error strictly less than the one of the corrected sample variance, but in general, I am not able to compute it, while I am always able to compute the corrected sample variance from my observations because they are based on this formula with the sample variance given this way. Okay? So I can compute it every time, the corrected sample variance, but the price to pay is that, okay, I will have a mean square error that will be a strictly greater than what I obtain in a wonderful world, okay? And the proof of this one, okay, so I won't do it because, okay, but you have the expression for this one that is given by this expression. You have the expression of the variance of the ideal sample variance that is given by this one. You take this one minus this one, that is this one minus this one, and you prove basically and very easily that you obtain a number that is strictly positive, okay? So to summarize what I have done in this first part is that, okay, I have show you a way to obtain an MBS estimator in the case of the expectation of a random variable using the sample mean. I have the mean square error related with this MBS estimator and a mean square error that allow me to build using Chebyshev inequality some intervals that I have called confidence interval. Okay. In the case of the variance, we have now at the end, okay, something that is called the corrected sample variance that may be computed from the observation, and that is an MBS estimator of the variance with a known, even if I don't have done the computation, a known mean square error given by the theorem A1. Okay? So I have the mean square error, and so I should be able to do also to build confidence interval in this situation. Okay? So here is the only thing I can say if I don't do more precise hypothesis. So if I only suppose that I have an n sample with particular conditions of integrability, it's the only thing I can say in great generality. In the second part of the course, I will see that I will be able to do more or to be more precise or to have more tools, but in a very particular situation, that is the situation where I deal with Gaussian random variable. Okay, so see you for the second part in the next video. Bye-bye.